Hello, welcome to C++ Advanced. Today we are going to talk about a special coding technique called resource acquisition is initialization. What it basically means is using objects to manage resources. Resources could be memory, hardware device, network handle, etc. Let's look at the example. I have a mutex mu, and in function A, I lock the mutex and then do a bunch of things and then unlock mutex. This is a pretty regular looking code, but there's a problem with this code. The problem is the statement of unlocking mutex may not be executed because the doing a bunch of things could return to function A prematurely. Even if it doesn't return, it may throw an exception, and in either case, the mutex will be locked forever. So we need a way to guarantee that the mutex will be unlocked once it is no longer needed. Let's look at our solution. The solution is to use the resource acquisition is initialization technique. Here I have a class lock. The class lock have a private data member which is a pointer to a mutex. And in the constructor of the lock, the mutex will be locked. And in the destructor of the lock, mutex will be unlocked. Now in function A, whenever I want to lock the mutex, I construct a lock and then do whatever things that I want to do. And by the end of function A, my lock will be destroyed from the stack, and then the destructor of the lock will be invoked. So the mutex will be unlocked. The conclusion we can take from this example is the only code that can guaranteed to be executed after exception is thrown are the destructor of the objects residing on stack. So in this example, the destructor of my lock is guaranteed to be executed. So our resource management needs to be tied to the lifespan of a suitable objects in order to gain automatic deallocation and reclamation. Another good example of resource acquisition is initialization is a shared pointer. A shared pointer is a reference counting smart pointer. It counts the number of pointer points to itself, and when that number reaches 0, the smart pointer will be destroyed. So now in function A, I created a new dog and assigned the new dog's pointer to a shared pointer PD. Once PD goes out of scope, or in other words, once there's no more pointer points to PD, the new dog will be destroyed. Let's look at another example. I have a class dog, a class trick, and a function train which trains a dog with some kind of dog trick. I have a function getTrick which returns a trick. Now in the main function, I invoke the train function with the parameter dog is created from a new dog, and the parameter dog trick is get from the getTrick function. Now, do you see any problem with this kind of code? Let's examine what happens in the train function's parameter passing. More specifically, this part of the code. There are three things happening. One is creating a new dog. Second thing is invoking the getTrick function. And lastly, construct a shared pointer and assign the dog to the shared pointer. Now, in C++, the order of the three operations are not fixed. It is completely up to the compiler. So, if the compiler decides to execute those three operations in this order, then there's a problem. The getTrick function might throw an exception. And if that happens, we have created a new dog, and the new dog has not been assigned to a shared pointer yet. So the memory of the new dog will be leaked. Now the conclusion we can take from this example is don't combine the operation of storing objects in a shared pointer with any other statement. In other words, put the storing objects in shared pointer statement to a standalone statement. So in this example, we'll extract this part of the code and then now our code is thread safe, because the new dog, once it gets created, it will be always assigned to a shared pointer, and there will no longer the possibility of memory leak. Our last note. What happens when the resource management object is copied? So in this example, I create L1 from Mutex MU and then copy construct L2 from L1. Usually the mutex is mutually exclusive, so it cannot be shared by multiple clients. So one solution for this is prohibit copying completely. We can do that by disallow the copy constructor and copy assignment operator from being used by our client. And to see how to do that, please watch my another session, which is disallow compiler generated functions, and we're not going to talk about that in this session. Solution 2. Sometimes the resource can be shared by multiple clients, and in those kind of scenario, all we want to make sure is that resource will be released appropriately once all the clients are done with it. So we need to implement some kind of reference count mechanism and to keep track of the number of clients who is using the resource. And we can do that with the shared pointer. In previous example, we have seen that shared pointer can take one parameter, which is a new created object that's stored on heap. The shared pointer constructor can take a second parameter, which is a deleter. A deleter is a function that will be invoked when the shared pointer is destroyed. And the default value for the deleter is the operator delete. So in this example, once the shared pointer PD is destroyed, the operator delete, the default value of deleter, will be performed upon the new dog. And a good thing about the shared pointer is the deleter can be customized to any function you like. And here we're gonna take advantage of that. Now let's look at the new implementation of the log class. Now it has a private date member P Mutex, which is a shared pointer to a mutex. The constructor of the log initializes the P Mutex with the pointer of the mutex as the first parameter and the mutex unlock function as the second parameter, the deleter. In the body of the constructor, it will lock the lock the mutex. So what this means is when the lock is created, it will lock the mutex, and when there's no more pointer points to P mutex, the mutex will be unlocked. Let's look at the example again. I create lock L1 from mutex and then copy construct L2 from L1. By this time, we have two pointers points to P mutex, and the reference count is 2. And by the time both L1 and L2 goes out of scope, the number of pointer points to P mutex will become 0. That means P mutex's deleter will be invoked, and then the mutex will be unlocked. So that completes our solution for our solution 2, which guarantees the unlocking of mutex once there's no client is using the mutex anymore. That's all. Bye bye.